All right, welcome everybody. Today we're going to talk about lesson number 79. This is section 10.6, and this section is called parametric equations. Depending on the level of physics that you've taken, you may or may not have heard of parametric equations. You can do these at a very basic, simple level, and then at a much harder level. We're going to kind of stick to the basics here in lesson number 79. Note there that for homework 79, it's only 5 problems, so certainly focusing on quality over quantity. There's also an important note at the bottom there. For the first 4 problems, there's a part A and there's a part B. For the part A, where you're asked to make a table, you should use the values -2 to 2 for any regular function, and then the values 0 to 2 pi for any trig function. That will make much more sense once you see the problems and once you complete this video. Please also note that this section 10.6 is not part of the conics take-home assessment, so you do not need to be responsible for the content in this video in order to complete that. A quick note before we go to 10.6, 10.5 we're not going to do. 10.5 is about rotation of conics. You're not really even going to do it next year in AP Calc, but it's just worth noting for one small reason. If you remember this general form of the equation, that's the one that we used for section 10.2 to 10.4, all about name that conic. Remember, we looked at whether or not there was 1 square term or 2 square terms, whether there was addition, subtraction, and whether or not the coefficients were the same. If you look at this version, that bxy, which we have not yet seen, if there was a bxy term, that means that there is a rotation of the conic. Whether or not you've realized it, every conic you have graphed so far has in fact been parallel to the x or y axis. So if there were to be some bxy term, your conic would actually be rotated so that it was not parallel to the x or y axis. And those are just kind of a couple of examples to show you what it would look like. Again, we're not going to do those this year. You're probably not even going to graph those next year, but you will see an xy term pretty often next year when you're asked to do things like take the derivative. So even if you don't have to graph the conic, I want you to at least be aware that it's a thing, and what it means is rotation of conics. So we're going to focus on 10.6, which is all about parametric equations. And basically the definition, parametric equations are equations that express 2 different variables in terms of a third variable called a parameter. Since you're expressing 2 different variables, you of course have to have parametric equations that come in pairs. The parameter is almost always t for time or theta to represent some angle. So let's go ahead and start with example 1. Example 1 gives you a context. Not every problem will. So again, that's just something you want to watch out for. So in example 1, we have the following set of parametric equations where x is the distance, y is the height, and then t is, of course, time. So that's our parameter. Here are our 2 equations. So x equals 40t and y equals -16t squared plus 40t. Hopefully that -16t squared is familiar as it comes from the vertical motion model. So if I wanted you to graph these and describe them, I have to give you these parameters to start. So on the next slide, if we want to go ahead and graph them, I am telling you to graph them from time equals 0 to time equals 2.5. Now, if you know the context of the problem is in fact time, obviously you would never use a negative value since that wouldn't make sense. So you generally would start at 0. In each problem, we're going to kind of use a different interval. And then for the homework, I will tell you which interval to use. And I would also tell you on an assessment. So if you want to graph a set of parametric equations, you're going to start by making a table of values. So your first either row or column, whichever way you want to do it, should always be your time values. And again, notice I am telling you to go from 0 to 2.5, and I have decided to use half seconds as my interval. If you used a half second versus a quarter second versus 1 second, the smaller your interval, the more points you have, which maybe makes it easier to graph. But whether you had used half a second or 1 second really wouldn't matter all that much. Then you're going to make a column for the x, which in this case they told you was distance, and the parameter was x equals 40t. So you're going to take each of these values of time and you're going to multiply it by 40. So hopefully it's very easy to see why this entire row becomes this row by simply multiplying each of the t values by 40. Then you're going to take these same t values and you're going to plug them into y equals -16t squared plus 40t. And again, that represents the height. While it takes an extra second, you're going to take 0 squared multiplied by -16 plus 40 times 0. That's going to give you this y value here. Then you're going to do 0.5 squared times negative 16 plus 40 times 0.5. That's going to give you this value here. So basically, when you go to graph a set of parametric equations, your first order of business is always to make a table. Then if you take those values and you draw them on a graph, here's what it looks like. You're going to take these actual XY points and you're going to graph them as ordered pairs, just like we always do, X going left to right and Y going up and down. But notice that I also added in these different values of T. That's just kind of a way for you to see exactly where the time values are. Based on this graph, we can see that both X and Y are continuous functions for time. And please note that this type of curve is actually called a plane curve. So that's a new vocab word. Another new vocab word has to do with the orientation. And this is where you're looking for the increasing values of the parameter. Basically, because of the fact that the time values are getting larger from left to right, that is where these arrows come from. These arrows, again, are called the orientation, and it's just basically a way for you to follow the graph. Where is it increasing? Where is it decreasing in relation to corresponding t values? So you are going to want to make sure that you add in that orientation. So something to note here, okay, the reason why we need parametric equations and what we're actually going to do with them, mostly next year in calculus, is if your parametric equations represent the path of a moving object, the graph alone is not enough for you to actually describe the object's motion. Yes, you could tell me its height at a certain distance, but you need more information in order to tell me the exact position, the direction, and the speed. So this is actually where the calculus comes in. So finding speed, direction, and position is a huge thing you're going to do next year using parametric equations. For now, you kind of just have to know that it's a thing. But again, the reason why we have these arrows is because we're actually looking to eventually find things like position, direction, and speed. So for now, you just have to be able to tell me where the orientation is, and then you'll leave the good stuff for next year. Here in example 2, notice that I am again asking you to sketch a curve. Notice that instead of 0 to 2.5, I'm telling you to do -2 to 3, and I'm only using 1 unit intervals. Again, it can vary from problem to problem. I will tell you on the homework and an assessment what to use. Here are my new parameters, X and Y. It does not specify that T is exactly time, which is why we're allowed to use negative values in this case. Notice that, again, my first order of business is to make a table. Notice that my table is going horizontally as opposed to going vertically. And again, that really doesn't matter. So you would take this -2 value for T, you would plug it into the X parameter, and that's how you would get this X value. You would take this -2 value for time, plug it into the Y parameter, and that's how you would get this point. You then are going to graph these ordered pairs as XY, and then notice that you're actually going to also put in the values of T, just so you know exactly at what time that is happening. In terms of the orientation, if you follow the arrows, again, the arrows are really just indicating the order in which the time values are going. So basically the order in which you fill in the table, the order in which you plot the points, you just connect them and show the arrow in terms of orientation. Something important to notice here is that this graph is not a function. It does not pass the vertical line test. I want you to know that that's perfectly fine. Depending on how many parametric equations you've seen in your lifetime, they actually can make some really cool pictures, and most of the time they're not functions, so perfectly fine if it isn't. Something else here, you can actually have 2 sets of different parametric curves that actually wind up giving you the same plane curve. So again, notice here that these are my 2 parameters, and I'm going from -2 to 3. Notice on the next slide, I have now given you a new set of parameters over a different t interval, but it has yielded the same exact graph that I had in the previous slide. One thing that you kind of would note here is that even though these new parameters give you the same graph, if you were to look at the orientation, okay, these arrows are actually happening more quickly, which actually means that the graph is being traced more rapidly, which actually tells you that the speeds in this problem would be different as opposed to the speeds in the previous problem. And again, not something you have to worry about for this year, but something you're definitely going to spend a lot of time on next year. So for now, just make sure that you know that it's a thing. Then there's another way that you can deal with parametric equations, and it has to do with eliminating the parameters, and those would actually be the directions. It would say eliminate the parameters. So what we've done so far is basically find XY points by selecting values and making a table. This is a great way to do it if you're only graphing something over a very small interval. So from 0 to 2.5 or from -2 to 3. That's a very small interval, and what we've done makes a lot of sense. If it turns out that you don't have a small interval, or if you don't have a finite interval, you obviously just can't sit there and keep plotting point after point after point. So if you're looking for a little bit of a time saver, you can basically convert the two parametric equations into one equation, which is called the rectangular equation, and this is called eliminating the parameter. There is a series of steps to eliminate the parameter. You're going to solve one of the equations for one of the parameters. Then you're going to substitute it into the other equation, and then you're going to simplify. So I've kind of laid those steps out for you right here. So again, this is going back to that same example. Here are my two parametric equations. You're going to solve one of them for t, and hopefully you would realize it would be much, much simpler to solve the second equation as to solving the first one. So try to do the simpler one. So if I solve for t, I get t equals 2y. I'm then going to take that substitution and put it into my other equation. I'm going to go ahead and perform the operation, and whatever you get here as your result, that is called the rectangular equation. And basically, when you have done that process, that is what's called eliminating the parameter. So once you wind up with the equation x equals 4y squared minus 4, it's basically a time saver. It's a way for you to more quickly plot points. It also gives you more of a picture of what's actually happening. Based on all the conics that we've done earlier in the chapter, if you see x equals 4y squared, that's how you know that this is going to be a parabola that faces to the right because of the fact that it's a positive y squared. So finding the rectangular equation kind of gives you a bigger picture of what the graph is actually doing, as opposed to just plotting the points one at a time. Something you do have to worry about, though, which we'll talk about in the next example, is what about the domain? So in the previous problem, we only did from -2 to 3. In this problem, the fact that you just have an equation means you could essentially graph any point. So how do you kind of resolve that? Well, we're going to talk about it in the next example. So here you're going to sketch the curve represented by those two equations by eliminating the parameter and then adjusting the domain of the resulting rectangular equation. Now, just FYI, you're not going to have to really worry too much about this tonight, or basically for us, this whole chapter. But again, it's just something you always want to keep in mind. So if we're going to eliminate the parameter, I want to take one of these equations, either the x equals or the y equals, and I want to go ahead and solve it for t equals. I know in the previous example, we solved the easier one. In this case, you actually want to solve the one that has the square root because you want to get rid of the square root. If you can get rid of that square root, that's just going to make your life much easier on the back end. So what I'm going to do is I'm actually going to square both sides. If I square both sides, I get x squared. If I square the numerator, I just get 1. And then on the bottom, if I square a square root, I'm going to get t plus 1. Then if you remember back to your algebra rules, if you have a fraction equals a fraction, you can basically flip each fraction because the reciprocal has to be true as well. You don't have to do it this way, but to me, that's just the easiest next step. And again, the reason why I would want to do that is because I'm trying to solve for t equals. So t plus 1 over 1, the 1 on the bottom is negligible. If I now solve for t, I'm going to get t equals 1 over x squared minus 1. So that is the first step here. I want to solve for t equals. And then to even make things a little bit easier, I'm going to find a common denominator. So the common denominator of 1 and x squared would, of course, be x squared. The 1 would stay a 1. And then this one here would become an x squared. So t equals 1 minus x squared over x squared. That's the first step of the process. Solve one of the equation for t equals. Now, the second step is to make a substitution. So you're going to take that t equals and you're going to plug it in for both of these t's in the second equation. So that is going to give you y equals 1 minus x squared over x squared over 1 minus x squared over x squared plus 1. So now we have a complex fraction. So if we want to try to get rid of this complex fraction, the first thing we're going to do is find a common denominator in just the denominator. So I'm going to change this 1 over 1 to be x squared over x squared. Hopefully you understand that that is, of course, equivalent. This is now going to be 1 minus x squared over x squared, big fraction. If I combine those, I simply get 1 over x squared. And then hopefully you remember how to get rid of complex fractions. You do your old friend, the keep, change, flip. So 1 minus x squared over x squared times x squared over 1. That's going to cancel out those x squared, which means that your rectangular equation, now that you have eliminated the parameter, is 1 minus x squared. And the truth is, to ask you to graph 1 minus x squared should actually be a relatively simple thing to do. You should, of course, know that that is a parabola that faces down with a y-intercept of 1 and x-intercepts of 1 and negative 1. In order to actually do the graph, though, this is where we have to kind of consider that domain. So on this next screen here, again, here's the rectangular equation I just found, 1 minus x squared. If you look back at these original equations, okay, you can see that based on this equation, t cannot be equal to negative 1. You can also see that based on this, t cannot be less than negative 1 or equal to negative 1. So basically, t has to be greater than negative 1, or else you're going to get a negative under a radical, which of course can't happen. So even though your rectangular equation does not appear to have any domain restrictions, because of the fact that your original parametric equations do, you have to take that into account when you actually go ahead and do the graph. So because of the fact that t cannot be anything less than negative 1, and because in this equation we actually know that it's time, that's why we're assuming that you're only going to graph the positive values, which is why you only see half the parabola and is why you see an open circle where the y-intercept would be. Again, whether you know for sure it's time, I get that maybe it wasn't as clear as it should be. Again, we're only going to do kind of an introduction to this topic. So on the homework, I'm going to tell you specifically what values of time to use, so you don't really have to worry too much about the domain restriction, again, other than just knowing that it's a thing. So here in example 4, you're going to be asked to sketch the curve by eliminating the parameter and then adjusting the domain as needed. Just a little something to keep in mind as far as the homework goes. 4 of the 5 problems in the homework have A and B. For part A, it tells you to make a table, which is what you did on the first 2 examples. Then in part B, it tells you to eliminate the parameter. So you're basically going to be doing each of these processes for those 4 questions. So just something to keep in mind. So here in example 4, and again, if you're feeling confident, you could go ahead and pause and try it. If not, you want to solve one of the equations for t equals. And again, we're going to 1, try to get rid of the square root, and 2, we would realize that to solve for the y equals would be much harder. So again, I'm going to start by squaring both sides, which is going to give me x squared equals 1 squared over, if you square a square root, of course it cancels. So x squared equals 1 over t. Again, my little trick says if you have a fraction equaling a fraction, you can go ahead and flip both sides. So that's basically how you get that t is equal to 1 over x squared. You're then going to take this and plug it in, substitute it into the second equation. So y equals 2 times 1 over x squared squared. And if you go ahead and square and simplify, that would, of course, give you 2 over x to the 4th. So again, hopefully you remember a little bit about what 2 over x to the 4th means. 2 over x to the 4th is a version of a rational function. Remember, a rational function normally looks like this with the 2 different pieces. You would have vertical asymptotes, you would have horizontal asymptotes, and depending on, if there were negatives or positives or big numbers or small numbers, that would kind of be how you would determine exactly how the graph would look. The fact that this is x to the 4th implies there actually would not be a negative piece to the graph. But again, how do we take this rectangular equation, which is 2 over x to the 4th, and how do we actually create a graph? Well, if 2 over x to the 4th is not enough to do it for you, then simply make yourself a little table. So t, x, and y. I'm going to choose 1 for t. If I plug 1 in here, x would equal 1. Oops. And again, if I then plug 1 into here, I would also then get a value of 2. And again, part of the reason why you have the parametric equation is you could kind of skip the t altogether and just use this. Another option, if you're going to pick a value, again, if you look back to the original t, because of the fact that it's a square root of t, I'm actually going to pick a perfect square, which is 4. That's going to mean that x is a half. If I then plug a half into here, a half squared is 1/16. 2 divided by 1/16 is actually 32. Doesn't matter where you get the points from, whether you get them from the original parametric equations or whether you get them from the rectangular equation, they're going to be the same regardless. If you take a look here, something to consider is if you look back at your original equation, the fact that this is the square root of t, that implies that t has to be greater than 0, and again, not equal to, because of the fact that it's in a denominator. So if the t value has to be greater than 0, then that also implies that in our rectangular version, x has to be greater than 0, which is why, again, we're only going to really wind up with half a graph. So if I use these points that I've chosen, so 1, 2 would be a point, and then 1/2, 1/32 would be a point, and it looks a little strange. And again, so here is part of the graph. And again, the orientation would go like this, because as you choose larger values of t, your x and y coordinates would be graphed 1, 2, 1/2, 32. So again, you're going to follow the arrows there. If I was to graph 2 over x to the 4th just straight up, there would be a second part of the graph reflected over the y-axis. But again, I'm not going to graph that because the original equation had a domain restriction, which means I have to take that domain restriction into account now as well. So eliminating, oh, I guess I left myself an extra screen for that, didn't need it. So then the next thing is what happens if you have to eliminate an angle parameter. So again, most of the time the parameters are either t for time or theta for some angle. So here's an example of what happens if it's an angle. So notice that I have now given you trig functions, and notice that I have told you to do it from 0 to 2 pi. So whenever there's angles and trig involved, you're always going to want to use 0 to 2 pi. And then a little tip over here. So if x equals and y equals, we're actually going to do something slightly different than what we did when we tried to eliminate something without an angle. We're going to start by taking each of these parameters and solve them for the trig function. So cosine of theta is going to be equal to x over 3, where sine of theta is going to be equal to y over 4. Then I'm going to use my old friend, the fact that sine squared plus cosine squared is equal to 1. So if sine squared plus cosine squared is equal to 1, that means that y over 4 squared plus x over 3 squared is equal to 1, which means that y squared over 16 plus x squared over 9 is going to be equal to 1, which means that this is my rectangular equation. And hopefully that looks familiar from earlier in the chapter. The fact that it's an addition and the fact that the two denominators are unequal means that this has to be an ellipse. So again, if you find that rectangular equation, just by looking at these two parameters, I don't know about you, but I frankly would have no idea what that graph is supposed to look like. So by eliminating the angle parameter and turning it into this, hopefully you can remember from just a couple of lessons ago that that is, of course, an ellipse. So on the next screen here, I have that ellipse for you. And again, I just put the x squared first, since that's the way that we're used to. Remember that when it comes to an ellipse, whichever of the variables has the larger denominator, that's how you know which direction it's going to open, which is why it's opening vertically. Remember, the larger value would be the a squared, which is why it would be 4 units up and down from the center, which is 0, 0. And then remember, of course, this would be your b squared, which is why it's 3 units to the left and right. And again, if you wanted to make a table, which again, you might want to, t, x, and y, whenever you have an angle involved, I would recommend doing 0, pi over 2, pi, 3 pi over 2, and 2 pi, just because that makes it a little bit simpler. And again, when you make that table, the orientation will be as follows. So you know the orientation simply based on the order in which the table appears and the order in which you would then go ahead and make the graph. So the last couple of examples here. So finding parametric equations for a graph. It says find a set of parametric equations to represent the graph of y equals 1 minus x squared using the given parameter t equals x. These are actually very simple. I only put one of these on the homework because it really is that simple. So here is what would be the rectangular equation. Let's say I'm telling you that t equals x. Well, that means you literally make the substitution. Y equals 1 minus, replace the x with a t, and then here would be one of your parametric equations. I mean, this would be the first one, and then this would be the second one. So honestly, a little bit lame, especially in a very easy example like that. One last one here, same thing. You're going to find a set of parametric equations given that same rectangular function, but now you're given a different parameter, the fact that t equals 1 minus x squared. 1 minus x. So you're going to go ahead and take t equals 1 minus x, and you actually have to solve this for x equals. So if you solve this for x equals, you're going to get x equals 1 minus t. Then you're going to take this and you're going to plug it in for this x. So you're going to get y equals 1 minus the entire quantity, 1 minus t squared. Do the FOIL. So 1 minus 2t plus t squared. Distribute the minus and combine like terms. That is going to give you a negative t squared, a positive 2t, and then the constants are actually going to cancel out. So those last two are probably the easiest ones.